So we're going to go through the process of transforming a line angle structure of a cyclohexane ring into a chair conformation. Then we will flip that chair because remember, every chair conformation has two different conformations to it. And then we will decide which of those two conformations is higher energy, lower energy, or if they're equal in energy. Okay. So let's start with a line angle structure. Let's start with a hexane, a cyclohexane. And we'll put a, we'll do a wedged bromine. Let's do a dashed methyl group. And we'll do a dashed fluorine. Okay, so 3 groups on the ring, and we want to transform this into a chair conformation. Now, the first thing I want to talk about is drawing a proper chair. You should think of any chair as 3 sets of parallel lines, because that's going to really help you visualize and determine how the groups should be pointed when you place them on the ring. Okay, so the way I always start is 2 sets of parallel lines. And I'm going to color code them as well. So we'll start with our dark blue lines, and I'm going to make them parallel like that. Okay. So that's our first set of parallel lines. Then we'll use a pair of parallel lines starting here. And what we're going to do is we're going to try to bisect the other line like that. Okay. So we're going to kind of aim for that, but we're going to stop a little bit more than halfway through. Okay. And we're going to do the same thing with this line. We're going to try to bisect this line like that, and we're going to stop a little bit more than halfway through. I realize here that I made this line a little bit high, so I'm going to use the magic of technology to just drop it down a little bit like that. But you get the idea. Okay, so there's 2 sets of parallel lines. And then our third set of parallel lines will just connect these. So that will connect to that, and this will connect to that. And if you've drawn it, accurately, those 3 sets should definitely be parallel. Maybe they're not perfect because nobody's perfect at drawing geometries like this, but basically that's how you get your shape. All right. Now, I always like to start with this carbon. That's my favorite carbon, and I'll explain why in a minute. When we deal with it, I'll explain why that's my favorite carbon. So I'm going to basically arbitrarily assign that carbon to be this carbon. Okay, so that's going to be our bromine carbon. And then we're going to go we're going to clockwise around the ring. So we're going to go from bromine to methyl to fluorine. You see they're going clockwise around the ring. We're going to do the same thing over here. We're going to go bromine, methyl, and fluorine clockwise around the ring like that. So that's kind of the plan. So I've arbitrarily assigned that that's going to be my carbon bearing the bromine. Now, where do we put the bromine there? Sure, but what direction should it be pointing? The bromine is pointing up. It's a wedged line, a wedged bond, which means it's pointing up towards the page, as opposed to a dashed line that's pointing down away from us to underneath the page, if you will. So what we want to know is, well, what is considered up on this carbon? Okay. Well, the axial groups, and I'm going to use a different color again for axials. The axial groups always point straight up or straight down. If it's an upward facing vertex, you see how that vertex is pointing upwards as opposed to this vertex that's pointing downwards. Okay. If it's an upward facing vertex, then axial is straight up. Okay. So that's going to be our axial group there. Now, if it's a downward facing group, then like this, if it's a downward facing vertex, then axial is straight down. Right? So we can kind of imagine where axial groups are going to go. This one's going to go up. This one's going to go down. This one's going to go straight up. And this one's going to go straight down. And you're correct if you are recognizing that they alternate, right? Because we have an upward vertex and then a downward vertex. So the equatorial is up, the axial is up, and then the axial is down. Then the axial is up, and then the axial is down. Now, the equatorial groups can be very difficult to place if you're new at this. So the way that I like to look at it, and the way I was taught, is that the equatorial group always goes parallel to the line, the color of the line, that's not touching your vertex. All right. So for example, in our carbon that we're looking at here, our pink carbon, it's a blue and green vertex, right? It involves the blue set of lines and the green set of lines, which means that the equatorial is going to go parallel to the red set of lines. And you're always going to place the equatorial groups going kind of outwards from the ring. So I'm going to put the equatorial group like that, parallel to the set of red lines, the color that the vertex is not touching. That's going to be our equatorial position. Okay, over here, we can do the same thing. This is a red and blue vertex. So our equatorial group is going to go parallel to the green set of lines, again, away from the ring. So we're going to go here, parallel to the green set of lines. All right. We'll do the same thing over here. This is a red and green vertex. So it's going to go parallel to the blue set of lines and away from the ring. So this way, there's our equatorial there. And over here, we've got a blue and green vertex. So we're going to go parallel to the red set of lines, like that. Over here, we've got a red and blue vertex. So they're going to go this is going to go parallel to the green set of lines. And then this is a red and green vertex. So it's going to go parallel to the blue set of lines. And this is maybe the hardest to see because it's got to go out away from the ring, right? So that's our equatorial. So there we've placed in the light blue bonds all the axial groups, and in the brown lines are all the equatorial groups. So back to our original question, which of these lines on our pink carbon is up? Well, hopefully you can see that the blue line, the light blue line, is up. The axial is up on that carbon. And this is also kind of important. Realize that axial does not always mean up, right? On this carbon, axial means up. But on this carbon, axial means down, okay? Same thing over here on our pink carbon. Brown is equatorial, and that's down. But over here, on this carbon, brown is up. Equatorial is up. So axial doesn't always mean up or down. It means one or the other. And equatorial doesn't mean up or down. It means one or the other. So it depends on what carbon you're looking at. Okay, but our pink carbon has the bromine and it's pointing up. Now, what is on the equatorial group? I should just point that out, right? It's not that nothing's there. That's our hydrogen, right? We've got a dashed hydrogen here, right? So I'll draw that in just for now. I won't draw every hydrogen, but just for reference, the hydrogen is equatorial there. Okay. Now let's move on. We're going to go clockwise around the ring. You want to be very careful about that. So our next carbon bearing the methyl group is 1 over, and it's 1 carbon clockwise around the ring. So same thing here. We're going to go 1 carbon clockwise around the ring. So this is now the carbon that's going to be bearing the methyl. So now we can ask, all right, is the methyl group going up or down? Well, clearly it's going down. It's a dashed line. So on our carbon here, it needs to be going down. So which of these bonds is pointing down? Well, hopefully you can see it's the axial group. Okay. So our axial, our methyl is going to be axial. And then what's the equatorial group? Well, again, we've got a wedged hydrogen. And that's up on that carbon. So our equatorial group here is hydrogen. Okay. All right. Then we're going to skip a carbon. We've got a carbon with just hydrogens. So we're going to skip one. And then we've got our fourth carbon with a fluorine. So again, going clockwise around the ring, we're going to keep going this direction. We're going to skip a carbon. And so this is going to be our carbon bearing our fluorine. Okay, so we ask ourselves, is the fluorine up or down? Well, it's down, it's dashed. And so what represents down on this chair? Well, on this atom, on this carbon. Well, it's fluorine, right? It's fluorine, it's axial, it's down. So our fluorine goes axial. So then our hydrogen is equatorial, okay? I won't draw on all the hydrogens. But now we've placed our 3 substituents. And what I'm going to do is I'm going to erase all the other lines, all the other bonds that we know are just hydrogens, okay? It's not that they're not there, and it's not that they're not bonded to anything. It's just that they're hydrogens, and so we don't care about them in terms of determining stability of the ring, because hydrogens are as small as you can get. All right, so there's our chair conformation, and that's only one of the 2 conformations, right? The chairs flip. So we want to draw the other chair now. And what I'll do is I'll go through the same process, but we're going to start with our first set of parallel lines leaning the other direction. So notice that in my first chair, my dark blue set of lines, and give me a sec here, our first set of dark blue lines was leaning towards the left, to the right, where they're leaning this way. Now we're going to start with them leaning the other direction. And I don't know why this is the case, but I always have a harder time drawing the chair leaning this way than I do drawing it leaning this way. And I think most people struggle with one chair over the other, but that's just the way it is. But it's the same process. So once we've got our parallel lines leaning that way, now we're going to draw our second set of parallel lines. So this is maybe sometimes the hardest to draw. We're going to take this carbon here, draw a line, and we're going to kind of imagine bisecting this line. We're going to try to hit it at a 90-degree angle, but we're going to stop about halfway through like that. And then we're going to start here. And same thing, try to bisect this line, and we're going to go about halfway through. And you see I've done it again. I started with this side a little bit high, so I'm just going to move it down. Use the magic of technology for that. Okay, and then we can connect our last pair like that, and that should be parallel to that, at least as close as you can get. It should be parallel. So there's our second chair, and sure enough, I think this chair does not look as nice as the first one, but we're going to live with it. Now, I told you at the very beginning that this first carbon that we did, this carbon is my favorite carbon to start with. I always want to have a substituent on that carbon because that's always going to be my point of reference. So why? Because when you flip the chair, what you are physically doing, if you had a model kit, for example, and you built a cyclohexane ring, you would see that it would make a chair. And you can actually flip a chair by popping it kind of inside out if you had a 3D model kit. Well, what we do to do that is we're going to grab this carbon and we're going to pull it down. So imagine we're just going to grab it and we're going to yank it down. And then we're going to do this carbon over here on the opposite corner, and we're going to yank it up. Okay. And that means that, and maybe I should have used different colors for these dots. Let's make that a pink dot. We'll make this a dark green dot, and we'll make this an orange dot. And we'll do that over here. It was the bromine was the pink, the methyl carbon was the green, and the fluorine carbon was the orange. Okay. So where does our pink dot end up? It ends up down here. Okay. When you flip the chair, that's where the atoms end up. Okay. So now it's easy. We just go around the ring in the same pattern, right? We went clockwise around the ring. Also, by the way, this orange dot was down at the bottom left, and when we pulled it up, you can see it's going to end up here. Right? So where does our dark green carbon go? Well, it's one carbon clockwise around the ring from the pink carbon. So now we've identified where all of our groups are going to go. Let's figure out if they're going to be axial or equatorial. Now, the rule for this is when you flip a chair, all of your axial groups originally end up equatorial, and all of your original equatorial groups end up axial. Okay, that's the rule. You'll also see that groups that were up in the first chair are up in the second chair. Okay, that's very important. A group that is up will always be up, even when you flip a chair. What changes is whether it's going to be axial or equatorial. Same with a group down. If a group is down in one chair, it's going to be down in the other chair, but it will change from axial to equatorial or from equatorial to axial. So you'll see that here. All right, so let's figure out where our bonds are, okay, where our axial and equatorial groups are. The downward facing vertex, remember this is a downward facing vertex, so it's going to have its axial group going down. So I'm going to make that straight down. Okay. Our green carbon will have its axial, it's an upward vertex, so it's going to have its axial group going straight up. And our orange carbon is an upward facing vertex, so it's going to have its axial group pointing straight up. Now, our equatorial, where do our equatorial groups go? Well, this is a dark blue and green vertex, so the equatorial group is going to go parallel to a red line. So we're going to go parallel to the red. This is a red and green vertex, so we're going to go parallel to the dark blue. Okay, and then this is a dark blue and green vertex, so we're going to go parallel to the red. Like that. Okay, now our bromine was up in the original structure. It's up in our first chair. And notice that if we pull that carbon down, it kind of follow that direction of that arrow. If we pull that carbon down, the brown line will end up pointing straight down. It'll be pointing axial. And the blue line will be pointing outwards away from the ring. So that's going to be equatorial. So down here, that's exactly what we see. The brown line ended up as an axial, and the blue line ended up as an equatorial. So on this carbon, what is up? Well, it's the blue line, right? It's the light blue line. So that's where our bromine goes. It's also up, right? So it was up an axial in our first chair. Now it's up an equatorial, right? And our hydrogen is now axial. It's on the brown line. I'm going to erase that, so we don't need that anymore. Our methyl group was down on the green carbon. So on our carbon now, which is down, well, axial is clearly pointing straight up. So our methyl group must be down. Notice that our line that was down was an axial originally. Now it's down equatorial. Okay, and so I can erase the brown line. All right, and then our fluorine was down, okay, and it was axial. Now, what's the down line? Okay, now down is equatorial. So our fluorine is now equatorial. Okay, and so we can erase that. So those are our two chairs. Let me erase the annotations and we'll put these next to each other. So these two structures are in equilibrium with each other. They flip back and forth. Okay, it's kind of like inverting an umbrella a little bit. It kind of pops inside and out. So equatorial. But now we can decide which one is more stable. Now in this case, it's quite easy. But the rule is that you always want the most and the most bulky groups to be equatorial. There is more room for atoms in the equatorial position. Axial groups can be crowded. So if you have a really big bulky group like a bromine or an iodine or a isopropyl or a tert-butyl or something like that, the big bulky groups want to be equatorial. Even if you have lots of small groups, they want to be equatorial. Okay, so everything wants to be equatorial, but if we can, we want to give preference to the big groups. Give the big groups as much space as possible, and then if the smaller groups have to be axial, then so be it. All right, in this case, our first chair had all the groups axial, and our second chair had all the groups equatorial. So in here, it's a pretty easy assignment that our second chair that we drew with all the groups equatorial is going to be the more stable conformer. Let's do another example. We'll do maybe one more. So again, we'll start with a ring, cyclohexane ring, and let's give ourselves let's do a T-butyl. TBU is the abbreviation for T-butyl. And then we'll do let's do a methyl up here. So here we'll just do two substituents. Okay. And same process as before, right? First, we'll draw our chair. And I'll go through it a little bit more quickly this time. So one set of parallel lines. Two sets of parallel lines. And then three sets of parallel lines. And we'll just start there. Now, again, I always like to start with a group there. And so I'm going to arbitrarily assign that to be my T-butyl group. And then notice that the methyl, the carbon bearing the methyl, is one carbon clockwise around the ring. So if this is our T-butyl carbon, then this is going to be our methyl carbon. Okay, now we know that this is an upward facing vertex, so it's going to have an axial up, and this is a downward facing vertex, right? So it's going to have its axial down. Okay, then the equatorial on the pink is going to go parallel to one of the red lines. So it's going to go like this. And then the equatorial on the orange is going to go parallel to a green line. So it's going to go like that. Okay. So there's the two relevant carbons that we've drawn out here. Then what direction is the TBU pointing? it's pointing up. It's a wedged line. So on the pink carbon, what is up? Well, it's the axial group. So this is, we'll put our T-butyl axial. Okay. Then on the, we can erase the other bond. Then in the orange carbon, the methyl is also up. It's a wedged line, wedged bond. So on the orange carbon, the up bond is equatorial. So we've got methyl equatorial. And then the hydrogen is axial. We don't care about it. We'll erase that. So there's our first chair. Let's draw our second chair. Same process. We're going to start with the first set of lines going in the leaning in the opposite direction. Okay. We'll connect, we'll bisect. Remember, imagine like you're going to go right through it, stop a little bit more than halfway through. Same thing over here. Imagine you're going to bisect it, stop a little bit more than halfway through, and I've done it once again. I'm going to adjust my lines just a little bit. Like that. And then we connect our last set. So that and that. And once again, it happened again. I think my first chair looks much better than my second chair. All right, so where did our carbons kind of move to? Well, remember, we always are going to pull this carbon down, and we're always going to pull this carbon up. Okay, this carbon is irrelevant in the chair because it doesn't have any bulky groups on it, so we can kind of ignore it. But that just means that this pink carbon ends up down here. And that's why I always start there. Like, I like that carbon the most because I know if I start there, that group always ends up there. And then I can just go parallel around the ring, or go clockwise around the ring, I mean. Okay, so if that's our pink carbon, then the next carbon clockwise is the orange carbon. So I know where our groups are, okay? All right, again, on the pink carbon, now it's a downward facing vertex. It was upward before, it was an upward facing vertex. Now it's a downward facing vertex. So that means that the axial is straight down, and the equatorial goes parallel to red, which is like that. And then on the orange, it's an upward facing vertex. So axial goes straight up. And equatorial goes parallel to blue, to the dark blue. So it's going to go like that. Okay. So the bromine, the T-butyl was axial up. When we flip the chair, it has to stay up, but it needs to go to equatorial. And you see indeed that now the pink carbon, the equatorial is up. So it was up, it stays up, but if you've drawn your chair correctly, it should switch from axial to equatorial. All right? So we can erase this bond. I'm just drawing them in so you see how the bonds line up. But once we've placed all the groups, the other ones don't matter. They're just hydrogens. Okay? Next, our methyl was up on the orange carbon. So now which one is up? Well, clearly axial is up. So that's going to be our methyl is going to be axial. And then we don't need our equatorial. That's just a hydrogen. Okay. So I'll clean that up there. And let's look at our two chairs next to each other. So now we've got a situation where each chair has one group axial and one group equatorial. but the groups are not equal in size. They're not equal in bulkiness. The T-butyl is a much more bulky group. Okay, significantly. It probably, of all the groups that we'll ever look at, the T-butyl is the most bulky. It's 4 carbons, a bunch of hydrogens. They're branched, so they're all pointing in different directions. It's a big, bulky group. So the T-butyl, being the more bulky group, is going to have a stronger preference to be equatorial. Okay, so this chair, the second chair, and it's coincidence that it's our second chair, but again, it's our second chair, happens to have the T-butyl group equatorial, so there's going to be a much greater preference for that chair than the other one. So the equilibrium is going to favor that direction. Basically, the chair is going to spend more time in the second conformation than it is the first. Okay, so that's how you do chair conformations. As you practice, you'll get faster at it. Okay, but hopefully a couple things have a couple take-home lessons here. First of all, always make sure that your groups have the same orientation in your initial structure and all your chairs. And when I say orientation, I mean, are you going clockwise around the ring from group 1 to group 2 to group 3 to group 4? Or are you going counterclockwise? You can go counterclockwise if you want. Okay. If you follow your groups clockwise, make sure they go clockwise around your chair. Secondly, make sure that you place your axial and equatorial groups in the correct location. I see so many chairs drawn where the groups are pointing in some direction that's neither axial nor equatorial. Okay, they're pointing in some V shape or something. I don't know. So in that case, it's impossible to evaluate whether you've drawn the chair correctly, because I don't know whether you mean this group is axial or equatorial. So make sure that you do draw your chair correctly. Make sure you place your axial and equatorial groups correctly. And that's what I use the colored set of parallel lines for. Axials are always up and down. Equatorials go parallel to the color that the vertex is not touching. And again, if it's an upward vertex, axial is up. If it's a downward vertex, axial is down. Third is always remember that up always stays up and down always stays down. Okay. If you change that, you're actually changing the molecule. We will learn more about that in a couple chapters. But if you change up and down, you're changing the molecule. And these are always representing the same molecule. So make sure up is always up and down is always down. But when you flip the chair, you will always have an axial flip to an equatorial or an equatorial flip to an axial. Okay. And then for evaluation, bulkier groups prefer to be equatorial.